Hello and welcome to the second of the lectures in this week 5 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the last lecture, we looked at and had a gentle introduction to fuzzy relations. We looked at the need for it and also saw some special binary fuzzy relations. In this lecture, we will look at compositions of fuzzy relations. Specifically, we will see that when we move from the classical relations to the fuzzy relations, we could interpret, there are different possibilities and we could interpret them differently when it comes to composing fuzzy relations. A quick recap of what we saw in the last lecture. So a fuzzy relation as a mapping from the Cartesian product of spaces to the unit interval 0, 1, and we say x is related to y under the fuzzy relation R for a binary fuzzy relation if xy belongs to the support of the corresponding fuzzy set or the fuzzy relation of the Cartesian products. We could again take the alpha cuts just like we did in the case of fuzzy sets and consider the subset that we get of the Cartesian product, and once again for increasing alphas the subsets would be telescopically decreasing. We could also resolve the fuzzy relation this way as we do for fuzzy sets. What is interesting is the way we have defined reflexivity and transitivity. Reflexivity is defined as R of xx is 1 for all x. Symmetry is clear. Transitivity, we always talk about T transitivity where T is a T norm. We have seen at least two special fuzzy relations. We have defined them. We are yet to see, which we'll take up in the next lecture. If a fuzzy relation is reflexive, symmetric and transitive, we call it a similarity relation or a fuzzy equivalence relation. These are two terms that you will see in the literature. And if it is only reflexive and symmetric and not transitive, we call it a fuzzy compatibility relation. Now, let's look at composition of functions and relations in the classical case. Let's have a function f from x to y and g from y to z. We typically write the composition of functions as g circle f. F acts first to take x to y and then g acts on it to take y to z. So typically we write it as g circle f as a function going from x to z. However, if we look at relations, in the classical relation case, if R is a relation on x cross y and S is a binary relation on y cross z, we typically write it as R circle S, which is a relation from x cross z to the set 0, 1. We will follow this convention when we are discussing relations. Now, the question is, if for a fixed x and z, how should R circle S of x z be? What value should it take? It is clear that this relation, which expresses whether an x and z are connected or not, related or not, is in fact, we expect it to be connected through some y in y and the relations R and S. So that means we decide whether x and z are related under R composed with S only through some y, and if that y were to be related to x under R and related to z under S. So perhaps we could look at it like this. So let's take an example. So I have a set x, set y and set z. A, B, C here, just PQ here and alpha, beta, gamma. So let's say that I indicate, so this is my relation R on x cross y. So B and C are related only to Q. Let's say P is related to alpha, P is also related to beta, but Q is related to beta. So this is the relation S. So now, if you were to ask R circle S of A comma alpha. What will it be? It is clear that A is related to P and P relates to alpha. So this is 1 because there exists a P in Y such that R of AP is equal to 1 and S of P alpha is equal to 1. Okay. So now then it is easy to write it like this, that R circle S of XZ is 1 if and only if there exists some Y such that R of XY is 1 and S of YZ is 1. That means X and Z are related to each other under the relations R and S by some Y. At least one Y exists. Now let's look at the compositions with fuzzy relations. So once again, these are mappings on the Cartesian product of xy and yz going to 0, 1. And now we write it as R circle S as a mapping from x cross z to 0, 1. The question again is, how do we decide the value of xz under the relation R circle S? Clearly, it is again should be connected through some y in y. Note that when we write in the case of fuzzy relations, x is related to y, binary fuzzy relation, we only say that R of xy is greater than 0. Even though we write it as R tilde, just to distinguish that it's a fuzzy relation, we will read it as R and slowly we will drop this tilde notation just to avoid the cumbersomeness of the notation. I think the context will make it clear whether we are discussing classical relations or fuzzy relations. So, under a binary fuzzy relation, we say x and y are related if xy belongs to the support of the fuzzy relation or the fuzzy set on this Cartesian product. That means we only know R of xy is greater than 0. So now what we want is, given that there exists a y such that R of xy is greater than 0 and S of yz is greater than 0, we want to say whether R circle S of xz is greater than 0, and if it is greater than 0, we want to be able to determine it. So remember, it is not only about saying whether it should be greater than 0 or not. What should the value be? For instance, it is perhaps we are given that R of xy is some alpha 1 and S of yz is equal to alpha 2. Then from here we are asking the question, what should R circle S of xz be? What value should it take? So now let's look at this diagram that we have here, and perhaps allow me to remove this. We are asking the question, what should R circle S of xz be for any given pair of x, z? To answer that, let's write these relations in the corresponding matrix form. So that means R, we would write it like this, A, B, C, P, Q, and S, we would write it like this, P, Q, alpha, beta, gamma. So this is your R and this is your S. And what we want is R circle S, which will be from A, B, C to P, Q, and R. Now, A is related to P and also Q, B only to Q, C also only to Q, and P is related to both alpha and beta, but Q is related only to gamma. Now, let us write what is R circle S from the given diagram. We know that A is related to alpha through P, so A alpha, beta, gamma. So A is related to alpha through P, 1. A is related to beta also through P, so it is 1. And A is related to gamma through Q, so this is 1. Now if you look at B, B is related to Q and it is related only to gamma. So B is not related to alpha or beta, and so is the case with C. So now, for the moment, let's assume that we are only given these two matrices which represent the relation. And from there, we need to come up with this matrix R circle S. How would we handle this is the question. Now we are given two matrices and we are actually obtaining another matrix. And all we are doing is using this composition operation. So now, in fact, it appears that what we are doing is some kind of a matrix multiplication. Look at this, 1, 1, 1, 0. So in matrix multiplication, essentially row into column, all we do is inner product of this row with the column, since the orders will match. So essentially we are doing sum of products, but here instead of sum and product, we seem to be using some other operation. What exactly is it? As you have seen, composition is somehow related to transitivity. So what we are doing is some kind of finding the transitive nature of these relationships between A and alpha through P. So essentially we are writing R circle S of A comma alpha. We say this is equal to 1 if there exists if some pair is 1. So some pair is 1. So some pair is 1 means as you vary over y, there exists a y such that for some y both of them are 1, and you do not really worry about if for some other y both of them are 1 or not. It can very well be, but otherwise also you do not bother. So essentially you can write this as alpha as minimum of, because you want both of them to be 1, only then it should be 1, minimum of R of A comma y comma S of y comma alpha max over y, because both of them have to be 1 for it to be 1, and for some y it should happen, not for everywhere, and that is where maximum is coming into picture. So now you see here, essentially all we are saying is R circle S of x comma z is max y element of y min of R of x comma y S of y comma z. So essentially what we are doing is what we call a max min composition, but we generalize it to max T composition. Of course, for any T norm, as we have seen in the case of transitivity, even here for any T norm, it would work in the case of classical relations, that is where the relations are either 0 or 1. Now let's apply this here and see whether it is true. Consider the first row, the first column, 1 1 is 1, 1 0 is 0, max of that is 1. Similarly 1 1 is, if you take these two ones and 1 0, then it is 1, minimum of 1 1 is 1, minimum of 1 0 is 0, and maximum of that is 1. So that's how you get this one. So essentially if you take these two matrices and if you do a max min composition or a max T composition, that is how you get the composition of relations. And simply we could use this in the case of fuzzy relations too, because now these are not just 0 or 1 values, these values come from the entire interval 0 1, and this formula is valid in the classical case too. So it is a very nice way of capturing what happens in the case of transitivity, and this is what is called sup-T composition, max T composition. In the case that y is finite, obviously sup becomes max, but otherwise in general, instead of talking about max min, we talk about sup-T composition. Now if you want to interpret this, if you fix an x and z, and if R circle S of xz is alpha, what does it mean from this formula? It means there exists a y in y whose connection strength through R and S to x and z respectively, through R to x and through S to z, is at least alpha. Remember, supremum of all of them. So now the maximum of what is happening inside this bracket is what you are taking, and T of this, just imagine T is min. So what would come out is actually something smaller than both of them, or at least the smaller among the two, or in the best case, that is when you use T is min. Otherwise typically we know that T norm is smaller than min. For example, if you take product, then it will be a product of these two, and these are numbers coming from 0 1, which means it will neither be r of xy or s of yz, it will be smaller than that. So essentially we are saying that if you use min, then we know that there exists some y whose connection strength is at least alpha to either x or z, at least alpha. Now, once we have interpreted this sup-T composition like this, let's go back to our matrix here. And let's try to generalize this slightly further. So what we seem to have is, when we are talking about composition, is this. So if you have R circle S of x to minus, we seem to have one binary operation here. I will denote it by certain forms, and another binary operation. So we took this as max and min, but why not some other operation? In the case of fuzzy relations, we have a lot of fuzzy logic operations. So why not try something else? So for the moment, let's assume that we use minimum here and the implication here. So that means instead of doing max-min composition, we are doing min implication composition. So I think it will be worthwhile to see what happens when you apply this composition in the classical case itself. So let's keep R and S same, and now we are going to apply this composition. So for the moment, I will indicate this by this. So we want to see what is R beta S. Now we are taking this into this. So 1 implies 1 is 1, 1 implies 0 is 0. Minimum of these two will be 0. So if we take A, B, C, alpha, beta, gamma, and A alpha is 0. Same. Look at A beta. These are same values. So 1 is 1 is 1. 1 implies is. Now we are looking at this and this. So we are looking at A and this. Once again, it will be the same. 1 implies 1 is 1. 1 implies 0 is 0. So minimum of these two will be 0. Now if you take the first row and the last column, 1 implies 0 is 0, 1 implies 1 is 1, but minimum of these two is 0. Now let's look at what happens for the rest of the cases. How is B related to alpha, beta, gamma? 0, 1 is 1, 1, 0 is 0 in terms of implication. So that means again minimum when we take it is 0. Now 0, 1 again it's the same 0. But something interesting happens in this case. 0 implies 0 is 1 and 1 implies 1 is 1. So minimum of these two is 1. Now since C has the same thing, this is what we get. Now if you compare these two compositions, they are quite different. Not just that, they are perhaps revealing also in some sense. Now A had at least one of them coinciding with alpha, beta, gamma. That means there exists a P such that AP is 1 and P alpha is 1, AP is 1 and P beta is 1, and AQ is 1 and Q gamma is 1. And that's how we got ones here. But now when you changed the composition to that of minimum implication composition, we see that that was not enough. And are we insisting then? So what does this capture? So when you are using min implication, what are we capturing? Are we saying that R circle R of xz is equal to 1 if and only for all y R of xy is 1 and S of yz is 1? Is this what we are capturing? Now if this is what we are capturing, then look at B and gamma. This is 1 1, yes, but we have 0 0. So perhaps then we need to modify this and say, okay, perhaps what we are capturing is really not, they should be equal to 1, both of them, but maybe that these are actually equal. That means x is related to z under this composition. Let's see, they become 1 if and only if through every y, r of xy and s of yz should be actually identical. But let's put this conjecture also to test. Instead, let's take here instead of 0, let's take 1. Now what happens to B gamma? 0 implies 1, 0 implies 1 is 1, 1 implies 1 is 1. So what we will get is still 1. And now you see here that r of xy is actually not equal to syz when y is equal to when y is equal to p. However, what it says is perhaps this could be a better way to capture it. But what we want seems to be that if through this composition, if x and z have to be related, then for every y, the connection strength of y to x should be smaller than the connection strength of y to z. Put in a more positive way, if x and z have to be connected under this composition, then for every y, the connection strength of y to z under s should be at least as big as the connection strength of y to x under r. So now you see here, earlier what we asked was, there exists y such that rxy is equal to 1 is equal to syz. So here we insisted on r of xy being equal to 1. We are still talking about in the case of classical relations and composition. We insisted that through some y, r of y should be related to x to degree 1 and also to z to degree 1. But it should happen just for one y. Whereas in this case, we have made this inequality, made this an inequality, and in that sense less stringent. But what we are asking is this should happen for all y. So there seems to be a nice trade-off. So when you want to actually capture this, for all y turns out to be minimum or infimum, and this you could consider it as an implication r of xy and syz. That's what we have captured. So we have interpreted it like this, but initially we had actually used implication. But if you want to come back, assume that you are using an implication which has ordering property. That means whenever this is smaller than this, that's going to be equal to 1. And that is when you will get 1. So essentially, you could think of it as using an implication with an ordering property here. So now this gives us another way of looking at composition, an interpretation, and through the interpretation we are getting another composition operation itself. This is called the Inf-I composition. I stands for implication, of course. It is given like this, and we will use this symbol, the left triangle symbol, and which is defined like this: infimum over y, I of rxy, syz. Note that we could use any implication here and any t-norm here, only this operation of supremum or infimum, they are fixed. To denote this, we are having this t above the circle and I above this left triangle. In fact, in the fuzzy set theoretic literature, this composition is also known as the Bandler-Kohout subproduct, as it was proposed by these two people, Bandler and Kohout. Both of these compositions are extremely important and they play an important role, especially considering the focus of this course, which is inferencing and clearly in fuzzy relational inferencing. Okay, so now we have come up with two different types of compositions. Now, are there others? Can we use, instead of a t-norm and an implication, can we use some other fuzzy logic operation? Yes, you can, but you need to be careful about interpreting them and where you can use them. For our purposes, these two compositions would serve more than quite well. Now let's look at properties of this composition. So let's take P or Pj indexed with J as fuzzy relations on X cross Y, Q and Qj are fuzzy relations on Y cross Z, and R is a fuzzy relation on Z cross W, and J is coming from an index set J. Well, if you consider this equality, it says P circle Q circle R is equal to P circle Q circle R. Essentially, it says that the circle T composition, the sup-T composition, is in fact associative. This should hardly be surprising because we are using a T-norm which is anyway associative and it can be actually inherited from there. Similarly is the case here. We see that the composition distributes over union, and in the case of intersection, we actually get some kind of subadditivity here. This final equality should also be interesting, where the symbol denotes transposition. So if you have a relation P from X cross Y to 0, 1, the transpose of it is from Y cross X to 0, 1. Essentially, we are transposing the corresponding relational matrix. So it says that with respect to the sup-T composition, P circle Q transpose is nothing but Q transpose composed with P transpose. Now, if similar kind of properties can also be expressed or explored and detailed for the Inf-I composition, but what is interesting is if you pick a left continuous T-norm and the corresponding residual implication IT, remember if T is left continuous, we can call the R implication as the residual implication of T or residuum of T. So if you fix T to be left continuous T-norm and I to be its corresponding R implication, and with the same relations coming from these sets, we have some interesting properties. Look at this. P with respect to the Inf-I or the Bandler-Kohout subproduct composition, P composed with Q composed with R is actually equal to P sup-T composition with Q and BK's composition with respect to R. So you see here, it doesn't have associativity as such, but it has some kind of an associativity, and it's with respect to the sup-T composition. Remember, T is left continuous and IT is actually its corresponding residual. Of course, it also has distributivity as we have seen earlier. But what is interesting is because of this distributivity, we also have the corresponding monotonicity. That means if Q1 is less than or equal to Q2, that means pointwise in terms of the relational matrix, if the numbers on Q1 are smaller than the numbers on Q2 at the same location, we can show that this is the kind of monotonicity that we have in the composed relations. And if P1 is less than or equal to P2, then the monotonicity reverses. Of course, this is also clear because IT as an implication is decreasing in the first variable and increasing in the second variable. But what is very, very interesting are these two properties. For this, let P be from X cross Y, Q from Y cross Z, and R from X cross Z. Look at this inequality. What does it say? P transpose sup-T composition with P composed with Q under the BKS product is actually less than or equal to Q. Now let's look at it in terms of dimensionality. So P transpose, P is from X cross Y. So P transpose is from Y cross X, P is X cross Y, Q is Y cross Z. So finally what you get is a relation on Y cross Z. So it is comparable, dimensionally it is correct. And look at this inequality. R is from X cross Z, P is from X cross Y, P transpose is from Y cross X. So this will give you something from X cross X only, and R is again from X cross X. So these are two inequalities which are of course dimensionally correct, but they show you the interplay between sup-T and the BK's subproduct composition when T is left continuous T-norm and I is the corresponding residual. These are two inequalities which play an extremely important role when we want to discuss fuzzy relational equation, and we will discuss them when we are discussing interpolativity of fuzzy relational inference going forward. And at that time, perhaps you will recall that we have seen this inequalities involving fuzzy compositions, relational compositions. Well, a quick recap. We have discussed compositions of fuzzy relations, and we have seen in the case of fuzzy relations, we could have different interpretations and hence different possibilities, which led us to talk about sup-T and Inf-I composition or the decayed subproduct composition. And we have also listed out some interesting properties which will come up again when we discuss inference systems, especially fuzzy relational inferences. What next? We had introduced fuzzy equivalence relation or similarity relation and compatibility relation. In the next lecture, we will look at how these special relations are going to be useful for us. A good source for the topics discussed in this lecture is once again the book by Claire and Yuan. You could also look into this book by Dinola and Sessa, which deals with fuzzy relational equations and their applications to knowledge engineering. Glad you could join us today for this lecture. I'm looking forward to meeting you in the next lecture. Thank you.